Well, these videos may not be fancy, but my design is to provide a little extra help to my students, and virtually all of the tools that I'm using are free except for this tiny little tablet that my family got me some time ago that I'm finally putting to good use. So here we go. This particular topic is one that comes up in multiple courses before we use it in the multivariable calculus sequence. So I kind of need my students to be familiar with at least the contents of this video before we get into the meat of the main subject later on, or the good vegetables for those of you that don't partake of meat. So, polar coordinates. Let's suppose we had a point here in the first quadrant, and this point has coordinates, of course, x and y. Another way to identify the location of this point is to look at its distance from the origin, although the symbol r turns out in polar coordinates does not always have to remain positive. Call that r. And then which direction do we go to get there? And instead of using like a slope or a vector like we have been using, some value theta. And so we want to convert the x and y values and write them as some value of r and theta. Now, the quick little conversions, if you were to complete this as a little right triangle, and this is the y value and this is the x value, we could use right triangle ratios from trigonometry, so the sine of theta would be the opposite leg from theta of this right triangle divided by the hypotenuse, and the cosine of theta would be the adjacent leg of this right triangle over the hypotenuse. And we also know that there's Pythagorean's theorem itself, that x squared plus y squared equals radius squared. And there's other trig ratios we could set up. If somebody wanted to talk about secant or tangent or the others, we can certainly do that. So the common way of writing these is so that we can find out, well, what does x and y actually equal in this new language? What do they become? So let me just scroll up here. And the common way of rewriting these, x would be equal to r times cosine theta, and y would be equal to r times sine theta, of course, Pythagorean's theorem. And just as a note, if you were to go back to that triangle, the tangent of theta, y over x, that is the opposite leg over the adjacent leg of that right triangle. We don't use it often, but there is one type of common equation where it comes in handy, so I don't want to leave it off the palette, but the ones I put in the box, those are the most common tools to use to convert between. Now, you need to know something before you pull out a calculator and decide you can do all conversions without thinking. Trig functions have two ways that you can work with them, forward and then the inverse direction. In the first quadrant, every trig function is positive. But in the other quadrants, they're either positive or negative depending on where you are on the graph. And when you use an inverse trig function, inverse trig functions can't go to all four quadrants. They can only go to two of them. I'm not going to review that in this video. You need to know that if you're not willing to sketch a little picture, you need to be prepared for having an incorrect theta. You'll never get r incorrect if you use the formula right. But theta may not get you to the quadrant you're looking for, so a sketch is almost always beneficial to making sure you don't have any little errors there. So here's what I'm going to task you with. I want you to pause in a moment here and see if you can take these three examples and convert each one into polar coordinates on your own, or do one at a time and come back and watch the next moment of the video. I'm going to hit pause myself here and work through these. I want you to do the same. Okay, I'm back. Let's see if we can't work through these one at a time. So the first example, we have the point 0, -3. And if you were to sketch this on the x and y axis, there's y and there's x, that point would be down here on the negative portion of the y-axis. And so from that we could gather that theta is equal 3 pi over 2 by kind of drawing it like this. Or theta could be negative pi over 2, or any number of other possibilities that would rotate around and end at that point. As often as I can, I'm going to stay close to the origin, and you could use either one of these for this example. And then also, besides the theta, well, what's r? Well, that's right. R in this case, this point here is just 3 units from the origin. So our coordinates, r comma theta, is 3 pi over 2. Or 3 comma negative pi over 2. There's the first example. Second example. We have the point -2, 2. And that particular point lies in which quadrant? That's right, second quadrant. And I'm going to sketch this out so we can see r and theta. That point there, we have two pieces of information to find. This one is simple enough that you may not need to use any actual calculation or formula. I hope that you would actually know, in this case, that theta is 3 pi over 4 in degrees. That would be 135 degrees. We'll predominantly use radian measure here. Now, what's the radius? That's a question mark. Yeah, there we go. Well, we know that x squared plus y squared equals r squared, and r will end up being the square root of 8. And you could probably feel your algebra teacher breathing down your neck there. To reduce that, that would be 2 times the square root of 2. But I'm just going to leave it like this, because I happen to know that the square root of 8 is almost 3, and I like it in this form. So our solution, our coordinates this time, r is square root of 8, and theta is 3 pi over 4. There we go, fully converted. One more example. Point 1, 3. First quadrant, we will find it. All right. R theta. So, many ways we can go about looking at this. If we were to build this as a right triangle, we would find that this particular triangle, that's 1 and that's 3, is not a triangle that has what we would call one of our known or fixed quantities for theta that we just know from memory, but that shouldn't slow us down. We could certainly find the radius without doing too much extra work. 1 squared plus 3 squared equals r squared. R will end up being, that's right, square root of 10. And then for as far as theta goes, we can use any trig function to find theta. In this case, my triangle is set up nicely, so if I found the tangent of theta, that would be 3 over 1, opposite leg over adjacent leg. So what's the notation for theta then? Well, that's right. We would use inverse tangent or arctangent of 3 over 1. Or you can call that inverse tangent if you prefer that notation. So our coordinates of this point would be square root of 10, comma, inverse of tangent of 3. That would be the exact value. You get a calculator out, you could find the approximate angle or radian measure. Arctangent of 3 would be the exact. All right, there we go. All done. 3 good practice examples. Good luck to you all.